Dr. Hansen here, and this is a preview video that I hope you'll listen to prior to coming to the acids and bases talks. It turns out that acids and bases are extremely important in terms of human life. We control the pH of our blood very precisely or we will die. And for that matter, we can look at the entire digestive system and see at all the different pHs that are tightly regulated and kept in order to do different parts of digesting and absorbing food. So we know pH is very important to life, and I want to talk about some chemical principles that underlie it. And first of all, I'm going to ask the question, why are carboxylic acids acids? And I'm going to illustrate this using acetic acid. This acid acts as an acid. What does that mean? I'm sure you all have heard that acids are proton donors. What does that mean? Well, for example, let's say that we have acetic acid floating around in your bloodstream. And the question is, will it primarily be in its acid form, the proton donor, or will it be primarily in its base form, the proton acceptor? So we have a conjugate acid and conjugate base. This is a pair that, depending on whether or not it's protonated, will determine what state it's in primarily. An acid, by definition, is normally in a base form. Since it is a proton donor, it will tend to give up its proton and be deprotonated, be in its conjugate base form when it's at physiological pH. So therefore I've drawn the arrow much bolder going toward the base form. And here I'm now using the molecule alanine. You'll notice there's an amine group here, but that won't appreciably affect the fact that the carboxylic acid will tend to be deprotonated in the body. As I mentioned, the equilibrium will be far to the right, and that's because a proton donor will tend to give up its proton and be a base at physiological pH. But they are in equilibrium, so there will always be a little bit of conjugate acid and a little bit of conjugate base. But my question is, why does a carboxylic acid give up a proton, whereas an alcohol, a hydroxyl group, normally won't? And there's a very fundamental reason for this. If you take the acid and give up the proton, that allows the electrons that are in this bond, let's take a look at them. We have electrons bonding the oxygen to the hydrogen. If they give up the proton and are now in the base form, that means that electrons on this oxygen can resonate down to form a double bond as these electrons resonate up here to form an oxyanion. So we can have an oxyanion here or here, and these electrons constantly resonate throughout this region, which means instead of being trapped in a small region, you have electrons smeared out. We know that like charges repel, so these electrons would much rather be smeared out than constrained into a small region. So there's two things here. Carboxylic acids are acids because they donate protons, because by losing the proton, it allows resonance and smearing out of negative charge. Also, I should point out that in this whole molecule of alanine, which atom is most electronegative? What would love to have electrons around it? The oxygens. So the oxygens are electronegative to begin with, and that's a good way to stabilize a negative charge. Now, I want to go just a little further with that. It's very important because I'm going to begin showing you compounds, and as soon as you see a carboxylic acid group on a pharmaceutical, you should immediately say, that proton's going to come off, and that will give you insight into how the drug is going to behave. It will help you in thinking about what resonance really means. You know, this double bond, it really is not two bonds directly between the oxygens. When you have a single bond, that's directly between the oxygens. As soon as you form a second bond, a double bond, what that means is that there's one bond between the carbon and oxygen directly connecting them. The other bond cannot occupy the same space, so it exists above and below the plane as pi orbitals. And again, here I'm showing a pi orbital connecting the carbon to this oxygen. And I'm showing that this oxygen has a pi orbital through it. And what can happen is that these electrons can slide over as these electrons become compressed up here. See, now, it'd be hard for one of these sigma bonds to move between this oxygen and this oxygen, but pi orbitals above and below just slosh back and forth all the time, so that in effect, they really are just one gigantic smeared out orbital above and below the plane. So this is a cartoon representation of resonance, but this is what the resonance really looks like. If you look at this structure here, which of these oxygens do you think is going to be most easily protonated to reform the carboxylic acid form, the conjugate acid form, rather than the carboxylate, the base form shown here? Well, you look at them, they're identical. There's no preferred place for the proton to come back in and interact with the cloud. Therefore, the only way to get a proton to stick on here in excess is to add a bunch of extra protons. So for example, if you take a solution that's buffered with acetic acid and throw in a bunch of hydrochloric acid, chloride is profoundly stable. The hydrogens come right off and they will begin to start converting some of the base into the acid form. So hopefully that helps you some in thinking about what a carboxylic acid is. Absolutely, I want you to recognize the structure of a carboxylic acid and recognize it is an acid, a proton donor, which means at physiological pH it's deprotonated. Now let's look at amines. Just as carboxylic acids, because the oxygen is so electronegative and can be stabilized when you have those two oxygens bound to one carbon, so amines tend to get protonated, so rather than existing in a normal ammonia-like form, they pick up a proton and become like ammonium. If you think about ammonia and ammonium, these electrons on the nitrogen have nowhere to resonate to. Oxygen can have lone pairs of electrons and it can be negatively charged because the electrons can resonate all over. This is a lone amine. If there were an oxygen up here, that would then be an amide, and then the electrons could freely resonate in, and the nitrogen would not pick up a proton. However, when you throw in a primary amine like this, or ammonia itself, that free pair of electrons has nowhere to go, and it will readily grab a proton. It's kind of trapped there, and it will readily interact and grab a proton, forming a base. So now, this is a fundamental underlying part of the pH talk, and I want you to now apply your knowledge and tell me, with this compound here, which of these protonated forms will be most prevalent in blood. Absolutely, you will have to do the same type of thing on the test. So, let's see. Here we have two acids, carboxylic acid, two conjugate bases. So will it be one of these two or one of these two? Well, again, physiological pH, as carboxylic acid is a proton donor, it will be in the conjugate base form. And the amine, which form will that be in? Well, again, amines at physiological pH act like bases. It will pick up a proton. So we get what is called the Zwitter-ionic form, meaning it has both a negative and a positive charge. Now, what's the overall charge on it? The overall charge is 0 because you have a full negative charge and a full positive charge. Since its charge is 0, it's overall neutral, will this diffuse through a membrane? And the answer is absolutely not. Neither of these charges is going to be comfortable in a lipid environment. Charges need to be in water where the water molecules can be oriented around them, with the hydrogens on the water molecules interacting with a negative charge and the oxygen atoms on the water interacting with a positive charge. So Zwitter ions will not go through membranes. In fact, nothing charged will go through a membrane. So a neutral molecule overall, but with a huge dipole, a strong negative charge at one end, a strong positive charge at the other end, completely water soluble. How about tyrosine? And I want you to pause and answer this. Which will be the protonated form of tyrosine? So now, okay, I'm going to move on, but I hope you pause and answer these questions because that will be what you'll be able to remember. If I just walk you through it, it won't help you much. So, first of all, we know that only about 1 out of 1,000 of the carboxylic acids will be protonated, so they will almost all be in the deprotonated form, which gets rid of the first column here and the middle column here, so we're down to 4 structures. Then we know that the primary amine will almost certainly be protonated and positively charged. Those two conditions eliminate the entire top row, and we're down to these 2 compounds. So the only remaining question is, what about the hydroxyl on the tyrosine ring? And I should point out that generally you see a hydroxyl, think of it as being protonated and neutral. However, if it is deprotonated in the case of an aromatic ring, those electrons can resonate down to form a double bond, and the lone pair can resonate all the way through the ring. Therefore, a hydroxyl attached to an aromatic ring is certainly more acidic than a typical hydroxyl, say as in alcohol, ethanol, or a sugar. So the pKa of a hydroxyl on an aromatic ring is around 10, so more than 1 out of 1,000 will be deprotonated, but that means that by far the most common species will have a positively charged primary amine, a negatively charged deprotonated carboxylic acid, and a regular hydroxyl. But it will, of course, resonate among all these other forms to some extent. So in other words, the answer is here. It is the Zwitter ion that has a neutral hydroxyl group. So this is the predominant species.